So let's start off. Let's continue. Why did I say let's continue actually and not really start off? Very
Yes, sir.
simply, we're going to be continuing on with something which you have learned in a previous chapter earlier, namely something from stoichiometry and how reactions work. So, for instance, let me directly look at what is going to be a solution over here. When you're going to be considering a solution is going to be something where you're going to be having, what to say, only one phase visible here, the liquid phase. And simultaneously, in this particular phase here, you're going to be having mixtures being possible. So mixtures in this are basically going to be mixtures in solution phase, in liquid phase, are basically what come out of the category of solutions predominantly. Now, when it comes to solutions over here, let's start off with understanding what are the variables which we need to start learning about so that we can keep track of, so that we can understand what is really happening. So you're studying this particular phase called the solution phase over here, which is mainly going to be a liquid phase, where you're going to be having the substances in mixture form in liquid phase over here. So when you're studying the solutions over here, you need to now look at mathematical variables, which are important to study here, which are basically properties or mathematical functions of solutions. What are these going to be? These are going to be your concentration
Concentration.
terms. So when it comes to the concentration terms here, all the concentration terms which are applicable for solutions come into this category here. You will have molarity, of course, as a starting. You will have molality. You will have normality. You will have mole fraction. You will also be having weight percentage. You will, of course, be having weight by volume percentage. You will also be having volume percentage. All your standard concentration terms apply over here, along with the weird ones also. When I say weird ones over here, you can have questions involving hydrogen peroxide. All right, you can have some questions involving them. In those questions for hydrogen peroxide, they might give you concentration from the point of view of volume strength. And then the rest of the question is going to be depending on the volume strength being converted into molarity and then solving. So if you don't know how to convert volume strength, you're straight away in trouble there.
Hmm.
Next up is going to be your, what to say, same analysis is applicable for sulfuric acid as well. Basically, oleum, percentage strength. They might play with that. They might give you that particular thing also. You'll have to convert the percentage strength meaningfully into whatever is going to be the concentration.
Hmm.
Now, so initially you're going to be having a quick recap of all of these concentration terms, which are going to be discussed over there in the chapter. Then we are going into more details. I'm just going to touch upon the overview of the chapter today right now. So next up is going to be how we are going to be having among these variables here. We learned about some of these variables now. These variables here, some of them are going to be useful for understanding some properties. Some of them are going to be useful for understanding other properties. For instance, when you talk about solutions over here, you've already learned about solutions a little bit in one other chapter before. Which chapter did you learn about solutions?
Ionic. Hmm.
Ionic. So ionic equilibrium was a chapter where you completely learned about solutions again over there. Right?
Hmm.
In that
Yeah.
chapter, which of these mathematical functions are important?
Mole fraction.
Mole fraction was important on ionic equilibrium, sincerely? You think and tell me? Only molarity, what the hell? Sincerely think and tell. Everything is concentration term, this concentration term, that correct?
Yeah,
Yes or
molarity.
no?
Yes. Yeah.
They're all molarity. There is no mole fraction there.
Not mole fraction. My good. I was thinking.
Hmm. So molarity is going to be the thing which is going to be constantly used over there.
Hmm.
Why is molarity more critical for ionic equilibrium? Because this is an equilibrium chapter. So equilibrium chapter is generally going to be having experimental data
Hmm.
measured at what condition usually?
Standard or room temperature.
What? Constant?
Yeah. Oh, pressure, concentration.
Constant temperature is the real thing which I'm looking for here. Pressure is not going to be the case.
Sir, not pressure would vary, no?
So why? Because equilibrium constant is a constant at a given temperature. So at a
Yeah.
constant temperature, you'll play around with it.
Okay.
Whereas now, when it comes to the next chapter of solutions here, which is going to be this new chapter here, where you're going to be learning more about solutions completely over here. This is going to be involving, what to say, understanding thermal properties of solutions. Think of this
So
chapter.
temperature is not constant.
So what does thermal basically mean?
Temperature is not constant, basically.
Yes. Thermal connections with solutions. So when you want to understand the thermal connection with solutions here, what do you now do here? You basically go into the next aspect over here, which is basically directly going to be the next set of mathematical functions which you're going to be doing. So here you're going to be varying temperature absolutely. So if we are varying temperature truly over here, then which property will be maintained a constant? Which concentration term is useful now?
Molarity. I
Huh?
mean, volume would,
Molarity is what type? It is moles per liter.
yeah.
Liter is
Molality.
volume of solution.
Molarity, yes. Yeah.
Right. So it deals with volume of solution. So if it deals with volume of solution here, then there is a problem now. Correct? What is the problem if it deals with volume of solution? Can you tell me? Have you tried heating a liquid?
Tried what, sir?
Have you tried heating a liquid?
Yeah, volume. I mean, it's gonna expand now. It'll.
That's correct. So volume changes.
Yes, sir. Yeah.
The volume is changing when you heat the liquid over here. What does that basically tell you? It
That
tells
means
you
it
polarity changes with change in
molarity
temperature.
will also. Yes.
Right. That means molarity is useless.
Yeah.
Right. So molarity is not that useful here. Molarity becomes useful. I mean useless. So which one is going to be useful now?
Molality.
Molality.
Yeah. Not non-volume dependent.
So
Most
this
actually.
becomes more useful now, and this becomes more useful now in this chapter. So you'll be having in this particular case here, the concentration terms that are useful are now going to be mole fraction and molality.
Whichever doesn't depend on volume.
Correct. Whichever is not going to be dependent on volume, they will become more efficient here. Of course, when those two become more important, weight percentage, weight by volume percentage also start becoming more important. Meaning, in some questions, they might give you weight by volume percentage or weight percentage, and then you'll have to do some conversions and then arrive at what you have to do. Starting point of the question. So this is basically the initial introduction to what you're going to be needing as a prerequisite to start off with the solutions chapter. All right. So what you're going to be learning in solutions, as I mentioned, is what happens to different types of solutions. First, we analyze each solution in detail, and then we discuss what happens to different types of solutions at different conditions, thermally speaking, when we are changing temperature. So to understand it, you need to first understand some basics of a solution. So let's say we're going to be having some water. All right, in a particular beaker. You need to understand vapor pressure. I think you already know vapor pressure, na?
Yes, sir. Yeah.
So vapor pressure is basically going to be nothing but if I'm going to be having some liquid, like say water, present in a container.
Keep it.
So if I have water present in a container here, in this container over here, when water is taken, what happens is you're going to be having, if I put a lid on top of this container here like this, if I put a lid on top of it, what happens is you're going to be having water molecules basically, which are going to be present on the liquid here, like normal. Under normal circumstances, what happens is water molecules are present on the surface here will escape into vapor phase. Right, they will escape into vapor phase. What is this process by which they escape into vapor phase? that is going to be evaporation.
Evaporation.
So you're going to be having regular evaporation happening here, which will allow the water molecules of the surface to escape into vapor phase. So in this chapter, you'll be understanding a little bit more about exactly what's happening there during the process of evaporation. And when they evaporate off, what happens over here is they end up getting accumulated in the air over here. When they get accumulated on the surface or in the region above the surface of the liquid here, what happens is they get collected up on top of the liquid over here. When they get collected up on top of the liquid, these gas molecules or these water vapor molecules now start exerting a pressure on top of the liquid surface. That pressure that they exert is basically what is going to be called as vapor pressure. So vapor pressure is effectively going to be when you have a lid only, you have vapor pressure applicable. Because if you're going to be having it in the open, what happens then? Atmosphere is outside. Outside air will basically be there. What will it do? It will push all of these water vapor molecules away.
Yeah.
As simple as that. So you're going to be having, in this particular case here, evaporation is going to be happening, which leads up to vapor being collected. That vapor then exerts a pressure called as vapor pressure.
Yes.
Now, what happens over here is you will end up having this process as you end up having more and more vapor molecules getting collected.
Pressure. Makes sense.
As more vapor gets collected, condensation, which is going to be the reverse of this process. Condensation, which is going to be the reverse of this process, also ends up increasing in the speed in which it is going to be happening. Eventually, we will have a particular point at which the evaporation and the condensation will both reach a nice, happy equilibrium. All right, they will both reach a nice, comfortable equilibrium. In which case, your equilibrium, which is going to be established, is going to be H2O liquid
Equilibrium
with H2O gas. This equilibrium is going to be having an equilibrium constant Kp.
Vapor pressure.
That is going to be your vapor pressure. This means vapor pressure for water or any liquid at a given temperature is a constant. Equilibrium constant, right? It's an equilibrium constant.
Yes.
Vapor pressure is an equilibrium constant.
Sir, how can we guarantee that it's same for all liquids?
No, it is not same for all liquids. Right? The property is available for all liquids.
I mean, this is like
have their own vapor pressures.
Sir, I mean to say like, how can we say that for all liquids that the Kp will be P?
What are the variables which you assumed over here? You think at that? What did we assume? We assumed evaporation happens. We assume condensation happens. Correct?
That's it.
That's all we assume. Right? We assume anything else. So what's the problem then? Right?
Okay. Yes.
The idea is very simple, Ram. Whenever you're coming across something where you have to test if a logic applies in other cases, you have to check what were the assumptions you made on that logic. If the assumptions you made were preposterous, involved something else, then yes, it will not apply. Here though, this is going to be perfectly applicable. Because the only assumptions we made were evaporation happens, condensation happens. Perfectly fair assumptions, right? No problems with making those assumptions. Okay. Now, next up. So in this particular case here, vapor pressure is an equilibrium constant. What does that mean? That means it is a constant for a given liquid at a given temperature. Clear?
Yes, sir. Yeah.
Oh, now, next up, we are going to be diving into what is going to be the next part of this entire thing, which is going to be, now you have understood that there are some more properties which are very important for liquids and solutions. First property being vapor pressure. Not just first, this is the only property. This is the main thermal property which is going to be connecting with everything else. Vapor pressure is going to be the main thermal property we are going to be studying now, and how vapor pressure changes. Good wind. I'm feeling nothing. Yeah. Okay. Next up. So now we have studied a little bit about vapor pressure. Now let's try to understand a little bit more about vapor pressure and a little bit more about solutions. So when it comes to solutions, now first things first, let's go back to the original definition. I talked about how liquid phase is what we are studying, and that we should technically, hopefully, have only one liquid phase. Meaning, we are looking at solutions which are like proper homogeneous mixtures, mainly, not heterogeneous stuff. The oil and water is not what we are examining right now.
Makes sense.
So let's try to study a little bit more about homogeneous solutions over here. So when we talk about these homogeneous solutions over here, how can we break them down into different types?
Homogeneous.
So homogeneous solutions, correct? Let's break them down into types now. First off, what's going to be happening? What are we having here first? Gas plus liquid.
Yeah.
Correct?
Yeah.
So gas plus liquid left, what is going to be the case there? Most important property is going to be, of course, solubility of the gas. Right? Because how is it that the gas is dissolving? And what is going to be happening here? Solubility of gas is going to be critical over there. This solubility of the gas is going to be studied by a law called Henry's law. Now, when you're going to be considering solubility of gases in liquids, the idea is very simple. We only look at it from the point of view of if I'm going to be having a gas in a liquid. Usually we take water. Water is our main liquid. We're not going to be changing anything from water there. So the idea here is there are two types of gases now when you're dissolving gas in liquid. First one is, of course, going to be the type which is going to be directly dissolving but not reacting with the liquid. So it's just dissolving but not reacting. That is going to be one category. Second category, three categories, maybe not two categories, three categories. Second category is going to be those which react with water, like say HCl gas. Consider HCl gas. The solubility of HCl gas will be extraordinarily high in water. Correct? Why? Because if it dissolves in water and reacts with water, as what?
Then forward direction.
Yes, acid. It reacts as an acid, correct? So this will basically dissolve in water to give you HCl aqueous, which will basically not stop. It will break into
H plus Cl minus.
Correct.
Sir, what is the exact definition of homogeneous solution?
Homogeneous solution, now you're going to be having only one phase being clearly seen. And it is going to be something which is also going to be properly, fully, evenly mixed.
So how is gas liquid?
Yes.
So gas plus liquid is only a homogeneous solution if the gas mixes with the
Yes, the gas dissolves in the liquid.
If only, yeah. Okay.
Gases dissolve now. How do gases dissolve in liquid? You tell me. They will dissolve evenly only, na?
Dissolve what?
How will a gas dissolve in a liquid? You think it will? You have to push the gas in.
Push the gas. Yeah.
Literally.
Yeah.
So if it reacts, it reacts. If it doesn't react, it just occupies the spaces in between, literally, as you have learned in small classes.
Yeah.
More or less. So that's basically what happens over here. And it occupies those spaces evenly, relatively. Because gas moves around completely inside. It has good mobility, na?
Yeah, okay.
So now, when it comes to this particular case here, one category is going to be the category which doesn't react with the liquid. Another category is, of course, going to be the category which will react with the liquid. The category which reacts with the liquid, its solubility is incredibly high because it's going to be reacting and it will keep going in forward direction, solubility wise. Whereas the category which does not react, that we can study using Henry's law. So when you talk about this Henry's law here, it talks about how solubility of a gas.
So you said there are three types, right?
Yes, the second category is going to be, of course, the one in between over here. Something which dissolves something which is not going to be, something which reacts partially. So if it's reacting only partially, then what will happen? If you can force the reaction in the forward direction in some way, solubility will increase.
Okay.
Right. There are three categories in the sense. First is going to be doesn't react at all. Second is going to be the one in between. Third is going to be the one which reacts properly, like HCl. So the in between one is going to be like a carbon dioxide type of shit.
Okay.
If I want to increase the solubility of carbon dioxide gas in water, how do I increase its solubility? I make the medium basic. Correct. Carbon dioxide gas, correct?
Yes.
So if I make the medium basic, what will happen? That will force the acidic reaction in forward direction.
Yes.
Dissolve.
Yeah, I know dissolve. Yes.
Right. So you have to start playing the game according to the equilibrium there.
Okay, that's nice. Okay.
You understand the idea here?
Yes. Yeah.
There seems to be fantastic rain. You might get your wish of the class ending on time by hook or by crook today. Okay. So solubility of a gas which is not going to be reacting at all. First category. That's what we are going to be studying using Henry's law. So in that case, the solubility of a gas depends on two factors there: temperature and partial pressure of gas above liquid. Basically, if you are going to be pushing the gas more forcibly into the liquid, more will dissolve. That basically means partial pressure of the gas above the liquid, if it is higher, more will dissolve. Quite obviously.
Yeah.
Right, literally. And temperature wise, what is going to be the case there? Higher the temperature, lesser the solubility. Very simply put, gas molecules have more energy.
Exactly.
You're going to be increasing temperature by more, correct?
So harder to react.
So harder to basically push them inside.
Okay.
All right. So you're going to be having solubility of a gas being something like this. So temperature, lower temperature, higher solubility. And partial pressure of gas above liquid, higher partial pressure implies higher solubility. So you learn this mathematically in a separate thing called Henry's law. That I'm not going to be going into. We'll look at that when you look at it. Next up is for gas liquid solutions. So you're looking at gas liquid solutions first. Next up, we'll start looking at liquid solutions now and solid liquid solutions. So first up, we will now consider liquid solutions and solid liquid solutions. Now, when it comes to solid liquid solution over here, what happens is by this time, we have started learning more about liquids and solutions. We are now learning more about each of these here. What have we learned about for a liquid here? We have learned that boiling point for a liquid is going to be inversely proportional to the vapor pressure of the liquid. That is what we have come to understand over here. Let's try to analyze this point a little bit more carefully here. What does boiling point mean? Define boiling point, please.
The temperature at which
liquid becomes gas.
Liquid becomes gas.
So,
but evaporation also.
Let's try to understand each thing patiently. So, what does temperature at which liquid becomes gas truly mean here? Because, as you just correctly pointed out, evaporation is a process which happens naturally at all temperatures. Liquid is becoming gas there also. Why is that not boiling point? What does boiling point truly then mean? So let's try to understand boiling from the point of view of vapor pressure. So what is going to be happening to vapor pressure as you increase temperature?
Decreases.
Stop. Think. What is vapor pressure really? Vapor pressure is going to be the
increases.
constant
it increases.
Let's discuss it in every different way possible. It's the equilibrium constant for what? For liquid in equilibrium with gas.
Increase in temperature favors.
Why does it favor forward?
Because first of all, the gas has more energy, so more collision, so more.
Stop. We have done thermodynamics recently.
Yeah.
Liquid to gas in the forward direction. What is enthalpy change?
Oh, liquid to gas. 1 second.
Liquid is becoming a gas. You have to supply energy or remove energy.
You have to remove energy.
Liquid is becoming a gas.
Sorry, supply energy. Supply energy. My bad.
So this is
Supply.
going to be obviously positive and endothermic.
Positive. Positive, yeah.
It's an endothermic reaction.
Yes, yeah.
The enthalpy change is positive.
Yeah.
The equilibrium constant. What will happen to it if I increase temperature?
Okay, so forward, yeah, it favors.
Forward direction is favored, equilibrium constant increases.
Yes, sir, yeah. Endothermic.
That is one way of looking at it and understanding it. There are lots of other ways of looking at the same thing. Let's now try to understand one other way. In this particular case here, this vapor pressure was basically the equilibrium between what and what?
Water, liquid, water, gas.
Basically, what processes? Evaporation and condensation.
Yes, yeah.
Correct?
Yeah.
If I increase temperature, what is going to be happening? My liquid molecules will have more energy. They can escape more easily into vapor phase.
Exactly, yeah. So
Easy.
evaporation is favored.
Correct. So evaporation is more easily favored. Evaporation will increase by a good margin. Condensation also will increase actually. Why? Because there are more molecules in vapor phase now.
But
each individual molecule is having more energy.
you have
So
to
for
remove
each
more energy.
individual molecule, it needs more attraction to basically now go into liquid phase. Because the individual molecules in vapor phase also have more energy now. So even though I have more molecules in vapor phase available, condensation has increased, but the amount it has increased by is lesser than the amount by which evaporation.
Same with endothermic, exothermic.
Correct, exactly. The same principle happens over here. So you end up having condensation increases, but it increases by like say 1x. Whereas evaporation increases by like say 2.5x. So you end up having more molecules present in vapor phase now.
Yeah. Okay.
Which means more pressure on top of the liquid.
Yes, yeah.
So as we increase temperature, what is going to be happening? Vapor pressure. Okay. What happens is this. At boiling point, think of boiling point as the temperature at which all of the liquid suddenly wants to go into vapor phase.
Yeah, all of the liquid, yes.
So what is going to be happening over there is very simply this. You're going to be having all of the liquid suddenly achieving an equilibrium with the vapor. So what is happening till now? What has been happening till now is the liquid is producing vapor. That vapor is being pushed down by the atmosphere from outside.
Yeah.
Correct. And the atmosphere is the one which is actually preventing the liquid from escaping out into atmosphere, out completely into gas. Right? Think. If I have a liquid present as a liquid, what is forcing the molecules of the liquid to stay attracted to each other? The atmosphere pressure on top of them.
Yeah.
So if currently the vapor pressure is now pushing against everywhere, it is not just pushing against liquid, it is also pushing against atmosphere also, correct?
Correct.
So at the boiling point, what happens is you're going to be having
equal atmospheric pressure.
Becomes equal to atmospheric.
Okay.
What happens if it becomes equal to atmospheric pressure? It completely pushes it away. And it escapes outward completely. Think of it as I'm going to be having, imagine a container. All right, I'm having a normal container. Imagine a container where there is some liquid present. This liquid is going to produce, what to say, particles in vapor phase.
Yeah.
Which are going to be stuck around like this. Of course, they will also be blown out by the wind also here and there. But what is overall effectively happening is atmosphere is continuously pressing on top of it. Right?
Yes.
So the atmosphere is constantly pressing down on top of it. At this point here, the liquid molecules in vapor phase now gain enough energy to push back against the atmosphere completely and still escape away.
So all the gas
All of them will keep getting out because now the equilibrium is now pushing continuously in the favor of gas molecules escaping.
Only thing stopping it is the atmosphere.
So originally what was keeping them tied down was the atmosphere.
Okay.
Like a blanket on top of them.
So then what about if there was a vacuum?
Think.
Then
Think. Exactly what you're thinking will happen.
it's
In vacuum, there is no vapor pressure applicable. There is no atmosphere, correct?
yeah.
There will be no liquid.
No liquid.
Yes, there will be no liquid. All of the liquid will evaporate off.
Oh.
Why?
Temperature is
No, vacuum, you keep removing the gas. What are you doing? You're doing the same principle.
Oh yeah.
Why did the liquid vaporize off completely at this temperature? Because as the vapor particles are getting more comfortable at pushing against the atmosphere and leaving, they leave. As they leave, this evaporation keeps happening more and more. Because there is no way condensation can happen now.
Yeah.
Why? Because molecules are escaping.
Forward reaction.
Against the atmosphere.
Yeah.
Leaving. समझ में आ रहा है कि क्या बोल रहा हूं मैं? That is the idea here is you're going to be having at the boiling point all the liquid molecules are comfortably easily going to become vapor, mainly because the moment they become vapor, they now have enough energy to push against the atmosphere and escape out.
Some more freedom basically. Yeah.
Yes. So they're not going to be getting trapped on the surface over there or on top of the container there. They will just fly away. They just escape away.
So then sometimes all of the water does not boil, right? I mean, does not evaporate.
Slowly, obviously. You think it happens slowly. And
Slowly, yes.
what happens eventually? When will all of the water not boil? It's called a sauna. Right?
Yeah.
What happens in a steamer or in a sauna?
It's like a closed area, right?
Yes, correct. So basically, you're having the enclosed region. That's why you start sweating a lot more.
It's like
Because a lot of
equilibrium.
water vapor present in the atmosphere.
Yeah.
Right? Same thing happens. Same thing happens here. Why does it not boil away? Well, very simply because of that. The entire atmosphere is extremely rich in water vapor then. That's why it probably doesn't boil.
Okay, got it. Yeah.
It had some ventilation, automatically it will boil off.
Correct. Yeah.
You understand the idea there?
Yes,
So
sir.
if it is vacuum, what will happen there? Liquid evaporates off fully. Because you're removing all the vapor. There will be no liquid.
Yeah, yes, sir.
That's basically what happens in a vacuum. Now, where did we suddenly? Why did we suddenly? Yes, So boiling point is going to be the temperature at which we are going to be having. So if I have to talk about what is boiling point here, it is going to be the temperature at which vapor pressure becomes equal to atmospheric pressure. So this is basically what is going to be your boiling point for a liquid over here. So this is going to be the next aspect here. So now we will start looking at other solutions. First up, we're going to be considering what to say. Next thing, let me quickly introduce the next characteristic here by discussing one type of solution here. So we will first start off with a solution of non-volatile solid in volatile liquid. So basically non-volatile solid now, let's say sugar and water. It's a non-volatile solid with a liquid water here. So what happens in this particular case here is very simply like this. So if I'm going to be taking a solution, let's say I'm going to be taking a solution which contains, say, in this case here, I'm going to use different colors. I'm going to call water the liquid as A, and I'm going to be calling sugar the other particles as B. I'm going to represent them with different colors. So water is going to be particles A. So most of the surface is going to be containing particles of A. But a little bit of it will contain some particles of B also. How much of it will contain what? Well, that is dependent on the concentration. Why? Because it's a homogeneous solution, correct? A proper true solution. So this guy became a true solution. This means this is homogeneous. This means evenly mixed. All right. So if it's going to be an even mixture here, now let's try to understand how evaporation is actually going to be happening and how vapor pressure is actually going to be really created. So let's say I'm putting a lid on top of this. So the lid is put over here. What happens is you're going to be having water molecules getting collected. Now the only problem here is this. The water molecules which are getting collected here are lesser in number. Mainly because evaporation, which was very much necessary for creation of water molecules in the vapor phase, is dependent on the surface because the surface phenomenon. It happens based on the amount of surface it is occupying. And vapor pressure is also a surface phenomenon. Right? Vapor pressure is also a surface phenomenon. Why is vapor pressure a surface property? Because vapor pressure applies on entire surface of the liquid solution, full surface. Whereas evaporation can only happen from the part where the liquid is present. Wherever the non-volatile solute is present, no evaporation can happen.
Correct.
Wherever the sugar particles are present, these guys are present, no evaporation happens over there. Because they are sugar particles, they are non-volatile solutes. Whereas wherever the water molecules are present, evaporation can happen. So evaporation is going to be
dependent on concentration.
Correct. So evaporation, which is going to be in turn deciding partial pressure of gas. Or you can say partial pressure of gas above solution. In this case, what gas am I talking about here? I'm talking about water only.
Water gas.
The partial pressure of water above solution. Evaporation is going to be deciding that. And that guy depends on surface occupied by water. Correct?
Okay, yeah.
Right?
Yes, sir. Yeah.
Which is going to be in turn dependent on mole fraction of water molecules.
Okay.
Because you're going to be having, this depends on surface occupied by water now. It depends on basically what then. It depends on what is the fraction of water present on surface.
Correct.
How much water is there?
Yeah.
It's homogeneous mixture.
Yeah.
That means the fraction of water present on the surface is the same as the fraction of water present everywhere else.
Yeah.
Right? Fraction on surface is going to be same as the fraction everywhere else. Which is this. Right? But my vapor pressure is going to be on the entire surface.
Okay.
So my evaporation actually decreases now, but my condensation does not change much. So you'll have a little bit reduced vapor pressure here in this particular case here when you're having a non-volatile solute in a particular mixture present over here.
So once again, why is vapor pressure a surface property?
Think it is pressure exerted on the entire surface.
Ah, yeah.
The pressure, pressure is a surface property, right?
My bad. Yeah, correct. Okay.
That's what. Nothing else over there. So you're going to be
So,
having this particular case.
why are you specifically writing above solution?
Where
Is it like pH, partial pressure of H2O? Sorry, vapor.
I'm just writing
pressure.
it because I have to make sure that you understand what is the context over here. It
Okay,
is
and
above the solution in the sense we are discussing the solution specifically here. So for this solution, we are talking about it.
okay, got it.
So it is in comparison with what? So if I'm going to be putting this out now in a more meaningful manner, let me put it up now here. So partial pressure of water as a vapor above the solution at given temperature T. This is going to be lesser than what was expected for it if it was a pure solid.
Oh, yes, correct.
Okay, so this will be lesser than partial pressure of water as vapor above pure water.
Yeah.
At temperature T. What is this actually? This is of course going to be nothing but vapor pressure.
Vapor pressure, yeah. Idea.
Or Kp.
Kp, yes.
This is also written by another terminology, pH2O naught.
Oh,
Yeah. So when you see pH2O, this particular fellow is generally written simply as pH2O or P liquid, whereas that is going to be given the terminology with a not over there.
No.
Now, the next thing to basically look at over here is this is going to be something for this particular solution is lesser. Right. So what happens next is you're going to be now having one very interesting property here, which is called as lowering of vapor pressure. What is this lowering of vapor pressure? This lowering here of vapor pressure can be written as the difference in the vapor pressure between these two. You understand the idea here? So if it is difference in vapor pressure between these two here, how will that be working out here? That will very simply work out as P naught of H2O minus P of H2O.
Yes.
Which, if we look at it from the expression here, we can understand that that is going to be obviously the parts where this sugar was on the surface there, correct?
pH 21 minus.
That is going to be the lowering part here.
Correct, yes.
Right. So this lowering here is going to be something which should be proportional to mole fraction of what?
The water. I mean, either water.
Not really mole fraction of solute over there.
Solute, yes.
Solute is my sugar over here.
Yeah. Oh, sorry, my bad. Yes. Correct.
Right. It is not really mole fraction of solute. It depends on particles of solute.
Occupying the upper surface. Yeah.
So when you end up writing it mathematically here, what happens is you end up now defining a new term called delta P. This delta vapor pressure is usually not written as delta vapor pressure, it is written as delta P. So we now define a new term called relative lowering of vapor pressure. This is a new mathematical function. If you end up writing this, this will come out to be equal to your mole fraction of solute. Literal.
Okay. Yeah.
Non-volatile. So this is a property which is, what to say, a function which depends on number of solute particles. in solution.
Yeah.
Fair so far?
Yes, sir. Yeah.
So this property, this type of mathematical function now gets a new name. Called as a colligative property.
Yes, sir. Yeah.
So what is this colligative property? A colligative property is a mathematical function defined for a solution. Right. So it's a mathematical property which gets defined for a solution, a mathematical function defined for a solution, which is going to be depending on or depends only on number of particles of solute in solution. This is going to be, obviously, now that I'm defining a new term for it, that means quite a few of the properties of solutions are going to be this type of.
Yes, sir. Yeah. Sir, just one second. Can I just come back? Just one.
You have a question or you having something to do?
Just a second, sir. I'll be right back.
Good.
1 second.
Okay. So basically, colligative properties are going to be very important when it comes to solutions. Mainly because when it comes to solutions, a large number of the properties of solutions are going to be behaving as colligative properties, where the properties are going to be mainly dependent on the number of solute particles present in the solution. So that is basically the idea over here. Let's continue on now. So the first colligative property is relative lowering of vapor pressure. Now the rest of the chapter is going to be more or less understanding the different properties associated with solution fluids. That's basically going to be a thing. You'll be learning about the next type of solution, which is going to be what to say, liquid plus liquid solution after this. And you'll learn the properties for liquid plus liquid solutions. And basically that's going to be the game. So you're going to be learning what happens when you're going to be having liquid plus solid solutions and liquid plus liquid solutions and the various properties of the. So more or less, this is going to be the entire chapter there. It is not going to be that complicated. As I said, some of the properties will be related to mole fraction, some of those colligative properties, and some of those colligative properties will also be related to molality. Why? Because both of them are mathematical functions which are not going to be dependent on temperature, and they are not going to be changing with temperature. So because they are a constant over temperature, you can use them and proceed on with understanding. Now, this basically is sufficient enough of an overview here because we don't have time. I do remember promising that I'll shut up by around 9:15 to 9:30. How is your situation overall otherwise?
It's regarding what? Like exactly?
School.
School. It's fine. Yeah. I mean,
No, I'm asking from the point of view of the say shuffling. You should have gotten a shuffling results by now.
yeah, I got the first batch.
Same batch still.
So,
So survived.
yeah. So they considered the entire year. That's why.
That's why you survived.
Yeah.
Seriously.
I mean, I think even if it wasn't for that, I would have survived. But like, not everyone else performed similar to me or like less.
What was your final score?
So they didn't give results. So they just gave batches.
What the? Seriously?
Yes, so they don't. They're weird, very weird. I'll go ask like the teacher. I
Huh?
wanted to know my. I was gonna go ask my teacher anyways for my performance in the reshuffling test. I'll yeah. If I get once I get there, I'll tell you. So yeah.
Oh, you're gonna go ask anyway and do during the okay, huh?
Yeah.
Cool.
If
But
they let me know,
this
I'll
is
tell you.
weird. Seriously, they didn't give you results, is it?
Yes, so generally they don't give the results for a reshuffling test.
Because they can dodge then.
Yeah, exactly. They have, they considered board results as well this time. I don't know why. Yeah.
Anything and everything to basically make it more vague.
Yeah.
So they still do the nonsense they used to do earlier then.
Yes,
So there are some paying customers in the first batch then.
yes, sir. Oh, no. I don't think so. I mean,
Possibly.
mainly our batch is still in our class. Only if like 4 people from other batches came.
Only 4 people from? Okay, maybe second batch then maybe there will be paying customers then.
My one of my friends got like the third batch and he talked to a teacher and got second batch.
Same teachers are teaching, I suppose, nah?
Same teachers for us. Yeah. for like the second batch, our math teacher is going to teach them.
Hmm?
Our math teacher is going to teach second batch, like for a change.
So basically same teacher, huh?
Yeah.
And chemistry teacher is also same
Yes.
in
Sir.
all first, second, and third.
Yes.
So all first three batches are same people only.
No, sir. Second batch and third batch. Sorry, only second batch. Our math teacher changed. Like our math teacher went to teach their batch.
Okay, he's not going. He's not been teaching them till now. He's going to teach.
He used to only teach our batch. Now he's teaching two batches plus first year batch.
Okay, first year batch, juniors. Okay, huh, fair.
Yeah.
Okay, so organic. How are things? They're going to be going full on.
Yes, sir.
What are your thoughts on that? Have you started revising? Have you started going through full, what to say, entire history of organic which I've covered so far?
Yes, sir. I went through the notes. Yeah. It was fairly okay.
Have you gone through it again now?
Again.
You should.
Okay. Yeah, I
You
was
should
gonna do
start
it
it tomorrow, right? It's full.
Yeah, tomorrow morning I'll do that.
June 4th is a holiday?
June. You don't.
Yeah, it
No,
should be a
sir.
holiday. Election results day is holiday for sure. Huh?
Second day. Okay.
Huh. Is it election results day? No, it is definitely a holiday.
Yeah, maybe. Yeah. Sir,
Then mostly I will catch up with you on that day, Tuesday.
sir, is it true that somebody got 360 in advance this year?
360 in advance this year.
Yeah.
Honestly, I haven't heard about where from where exactly.
Alan.
Alan.
Yeah.
Possibilities there.
Okay.
But I'm not 100% sure. Because this time, from what I heard, the max paper was doable, nothing too exceptional. Chemistry was a tough one. So if the kids could have done chemistry well, they would have survived off. Possibilities there.
Sir, also like for solutions, like how like common is it in mains and advance?
Repeat. This
Solutions.
chapter,
Yes, sir. Yeah.
this chapter appears relatively only. What to say? There will be a question.
Main.
Mains, definitely there will be one question. And advanced, yeah, usually there will be a question. Sometimes they'll combine it with another chapter and what does they make the question, which will make it even more trickier. For instance, in advanced, they like to combine it with thermodynamics. They like to combine solutions with ionic equilibrium. And sometimes they can combine solutions with ionic equilibrium and chemical kinetics together. So when you end up combining it with another chapter, it becomes more potentially deadlier as a question.
Yes.
So it's a very easy topic to be combined with many topics.
Okay.
Almost all the reactions you learn are in solution form.
Yeah, that's true. Yeah, man.
So obviously it has enormous potential for combination.
Yeah. Yes.
That's basically it. What else? Yeah, we will close the session here. Any questions you have to ask before we disperse? You're going to be going into a very grueling round now. There will be no breaks.
Yes.
Your vacation is over.
Mm.
Whatever freedom you had is done. No more breaks till the game's officially, at least partially flagged off.
Yes.
So, what are your thoughts? What are any questions you got?
Nothing. Sir, nothing.
All right. Bye bye. Have a good night. I will see you on Tuesday.
Yes, sir. Yeah.
Or Wednesday, mostly.
Yes.
Wednesday, anytime. Tuesday also mostly.
Okay, sir.
Bye bye.
Thank you, sir. Good night, sir.
Have a good day tomorrow.
Thank you, sir. Yeah. You too. Yeah.